Good morning. Hello. Hello, hello. Hello, hello, everyone. So I am reading this book on the history of Western philosophy, and one of the first philosophers was Pythagoras, who, came up with the Pythagorean theorem. And so I learned that in addition to, his philosophy and his mathematics, Pythagoras also founded a religion. And one of the rules of this religion was don't eat beans. So I thought that was just like a really random rule to have for a religion. Like, why wouldn't you eat beans? And so Pythagoras lived, he was Greek, but he lived in Italy for his life. So I have a friend who lives in Italy, and I told her, I was like, do you know Pythagoras? Do you know he founded a religion? And one of the rules is you can't eat beans. And she's like, oh yeah, that's because of Fauvism, which I've never heard of that before, but there's a genetic condition called Fauvism, which is a metabolic disorder. And basically, if you're in the same room as fava beans, you could die if you have this genetic disorder. And so it's thought that one of Pythagoras's friends had Fauvism, which is why he made that rule in his religion. And apparently, even to this day, in Italy, a grocery store has to state outside that it has fava beans, if it does. So maybe it's a more common genetic condition in the Mediterranean than it is here, because I've never heard of anyone being, brought to the brink of death by fava beans. It's kind of funny. All right. Looks like everyone's here, so I will start my review. Should I make a pun about it? They're my favorite. Okay. All right. So let's talk about thermal physics. This is the first topic for our review. So we learned that that there's this thing called heat, Q, and heat is a form of energy. Heat is a form of energy, and the amount of heat that is added. The stream is laggy. I restarted my router this morning, and I don't know if there's anything I can do about it today. I think it might be the weather. A lot of moisture in the air. Excuse me. So Q is heat. All right. And And the heat added to a material is proportional to its change in temperature. Okay, so this is the mass of the sample. And this is the specific heat capacity. Which is, and then this is the change in temperature. So basically what this equation says is that the amount of heat that you add determines the change in the temperature, but it also depends on the amount of material that you're heating up. More mass means it's going to take more heat to raise the temperature. And then also there's this thing called the specific heat capacity, which is sort of an intrinsic ability of a material to absorb heat. Okay, so this equation assumes that there is no phase change. Okay, because what happens is during a phase change, so for example, boiling, if you start out with a pot of water, the temperature of the pot of water is going to rise, according to Q equals mc delta T, until you get to the point where it starts to boil. And then once it starts to boil, the temperature plateaus at 100 degrees Celsius. Okay? And it's only after the liquid has completely boiled off that the temperature can start to rise again. So during a phase change, there is no change in temperature. And so we have a second equation, which is Q equals mL, where L is called the specific latent heat. And this is the heat required to change the phase. Okay. So yeah, the amount of heat required to change the phase is just set by the type of material and the amount of material. Okay, but the temperature is staying constant during that process. So we use this to sort of solve calorimetry problems. And so calorimetry problems, you usually have a closed system. So your equation is usually of the form 0 equals Q1 plus Q2. This would be two objects. So basically, one object is going to gain heat. The other object is going to lose heat until they reach the same final temperature. All right. So we could use this equation, to predict the final temperature. All right. So for example, we could have M1C1 delta T1 plus M2C2 delta T2 equals 0. That's one application of calorimetry. We could also talk about, if we want to know what is the final temperature going to be. So you could have a single sample, not multiple samples exchanging heat, and you have the heat added is equal to the heat required to heat a liquid, then the heat required to boil it, and then once you boil the liquid, you're left with a gas, and so then you have to heat the gas. So you can have these kind of multi-step processes where you have, this is M1C of the liquid times delta T for the liquid phase, plus M1L plus M1C of the gas phase times delta T of the gas phase. So you have the total amount of heat added is heating a liquid and then boiling it and then heating the gas. So this is just one example. You could have many different transitions. You know, you could start out as a solid and then melt or something like that. So this is an example of heating a liquid, boiling it, and then heating the resulting gas. So then we talked about ideal gases. Ideal gases have they obey the ideal gas law, PV equals nRT, where P is the pressure, V is the volume, N is the number of moles, R is the ideal gas constant, which is 8.31 joules per mole per Kelvin, and T is the temperature in Kelvin. That's important. It's the temperature in Kelvin. So I'm not going to go over that too much because you already know it from chemistry class. The total amount of internal energy of an ideal gas is 3/2 nRT. Okay, so this one you probably didn't learn in chemistry. So this is the internal energy, remember, is the kinetic and potential energy of random molecular motion. Okay, so basically the hotter the gas is and the more gas you have, the more energy it has of those random kinetic energy of the atoms. We talked about PV diagrams. And in a PV diagram, you have pressure on the vertical axis and volume on the horizontal axis. And if you look at a particular point, okay, that particular point defines the state of the gas. And we could tell what the temperature of the gas is from the ideal gas law. So that would be PV over nR. So we know what the temperature is when it's right there. If the gas undergoes some kind of a process like this, it moves from one spot to another, the area under the curve is the work done by the gas. Okay. If it does a closed cycle, like a loop, then the area enclosed by that loop is the work done by the gas. Okay. There were two gas processes that are probably the more important of the two gas processes. One of them was called an isothermal process. And for an isothermal process, you have that P times V, P initial times V initial equals P final times V final. And this is a process where temperature is constant. Okay. Another process we learned about was called an adiabatic process. And that is one where the amount of heat added to the gas is 0. So it's just completely, you know, if you change the volume of a gas while keeping its temperature constant, you can imagine if you increase the volume of a gas, the temperature is going to drop. Okay? So in order to increase the volume of a gas while keeping the temperature constant, while it is expanding, you have to be adding heat in. Okay? So for an adiabatic process, if it's an adiabatic expansion, you don't add any heat in. and so it obeys a different law. So P in that law is P initial times V initial to the 5/3 equals P final V final to the 5/3. Okay, and so why that is beyond the scope of this class, but it's true. Then we talked about the laws of thermodynamics. Okay, and so there's the first law of thermodynamics, which basically is a statement of the law of conservation of energy. It says that delta U equals Q minus W. Okay, so delta U is the change in internal energy of the gas or of the object. Okay, so you can think about it. If the amount of energy changes, then either heat was added or removed, or it did work. Okay, so that's all this is saying, is that, you know, if you, for example, if 1 joule of heat is added to the sample and the sample does 1 joule of work, then that heat just immediately became work and nothing changes in the internal energy of the gas, so delta U would be 0. Okay, so all this law is doing is accounting for changes in energy. Okay, it's saying that heat is a form of energy. Then there was the second law of thermodynamics. So we defined this thing called the entropy, and the entropy is denoted by S. The change in entropy is the heat added to the sample divided by the temperature. Okay. And so the delta S of the universe is going to be the delta S of the first object in the universe plus the delta S of the second object plus ... however many objects there are. And that has to be greater than or equal to 0. That's the second law of thermodynamics. And one of the consequences of the second law of thermodynamics is that if we think about a process, a cyclic process with a gas, for example, the efficiency, which is denoted by epsilon, is equal to the heat added, okay, or sorry, I'm goofing here. The efficiency is equal to the work done by the gas divided by the heat added to it, okay? And the second law of thermodynamics says that there is a maximum efficiency, okay? And it's equal to 1 minus T low over T high, where T low is the lowest temperature in this gas process and T high is the highest temperature in the gas process. Okay, so the second law of thermodynamics limits efficiency. Okay, so the last topic from this semester is waves. Okay, and so we started off by talking about simple harmonic motion. And simple harmonic motion means that the position as a function of time is a sine or a cosine. So it looks like this. All right. So the amount that the graph goes above the horizontal axis, that is called the amplitude. Okay. And the time between peaks is called the period. Okay. So those are important things about simple harmonic motion. And so there's an equation that will result in simple harmonic motion. That equation is minus omega squared x equals a, where a is the acceleration, all right, and x is the displacement from equilibrium, and omega squared is a constant depending on the properties of the system. Okay, so whenever you have this equation, you're going to get position as a function of time that looks like this. So omega is related to the period of the simple harmonic motion. So the period is 2 pi over omega. So basically, you would do Newton's second law, get an equation of this form, figure out what omega squared is, and then use that to get the period. All right. So then we talked about traveling waves. All right, and so traveling waves you could think of as sort of a collective simple harmonic motion. All right, so if you have, let's say, a water wave, and the water wave is headed that way. All right, let's say there's some people swimming in the water. So if we look at what is the position of this person as a function of time, well, as the wave passes by, they're going to bob up and down. So they're going to have a position as a function of time that looks like this. Same thing with this person. They're going to have a position as a function of time that goes up and down. So each of these people are undergoing simple harmonic motion, but when one person is high, the other person is low. So they're out of sync simple harmonic motion. So basically when you have a wave, you have the entirety of the medium is undergoing simple harmonic motion, but it's all out of sync with each other in such a way that it makes this wave motion. And so the space between crests is called the wavelength. Lambda. There's the frequency, which is equal to the number of oscillations per period, or per second, I should say. This is important for the final. Make sure you know that number of oscillations per second. Excuse me. Okay, and so for a traveling wave, you have this equation, V equals lambda F. All right, and so V is the wave speed. So it's how fast is this crest moving. So that's an important equation. One of the things about waves is that the energy or the intensity of the wave is related to the amplitude squared. So the intensity is energy carried by the wave, essentially. So if you double the amplitude of a wave, you're increasing the amount of energy carried by it by a factor of 4. You're multiplying the energy by a factor of 4. The intensity is also related to 1 over r squared, where r is the distance from the source. And so what this equation is saying is that the further you get away from the source, the weaker the wave is, the less the intensity. Okay, So then we talked about musical instruments. And there were three types of musical instruments. There was the okay, so there was the closed. There was the open, and there was the open-closed. So I'm going to draw what the harmonics looks like for each of these. So for a closed instrument, you have the first harmonic that looks like this. You have the second harmonic that looks like this. This is the first harmonic, this is the second harmonic, and so on. Closed instruments are usually stringed instruments. For your open instruments, they are like tubes. And your first harmonic looks like an hourglass. Okay. Your second harmonic. To go to the next harmonic, you always add a football. That. So this is your first harmonic, your second harmonic. An open-closed instrument is typically a wind instrument as well, but it's capped at one end. Okay. And so the first harmonic looks like half an hourglass. The second harmonic, you add a football like this. Actually, that's not the second harmonic. So for an open-closed instrument, you only have odd harmonics. So for each of these two, the wavelength of the nth harmonic, okay, the wavelength of the nth harmonic is 2L over n, where n can be any integer. And the frequency of the nth harmonic is NV over 2L. All right, where n can be any positive integer. Okay. But for an open-closed instrument, the equation is slightly different. Okay. And so we had that the wavelength of the nth harmonic is 4L over n, and the frequency of the nth harmonic is NV over 4L, where now n can only be an odd positive integer. Okay? So the last thing we studied before the end of the semester was electromagnetic waves. Okay. Electromagnetic waves travel at the speed of light, which is c, and that's equal to 3 times 10 to the 8th meters per second. Electromagnetic waves are transverse waves. Instead of longitudinal. So a transverse wave is one that vibrates perpendicular, where the medium is vibrating perpendicular to the direction of travel. So if there's a wave coming directly towards you, it's going to be vibrating either like this or like this. Okay, so it's like snaking towards you. I sort of think of it like a snake. A longitudinal wave is one that vibrates parallel to the direction of travel. So it's kind of like, transverse waves are kind of like snakes, like they slither. And what are the ones that kind of bunch up like this, like a caterpillar? Longitudinal waves are kind of like caterpillars. All right, so they scrunch up. They kind of go. like that. So the thing about transverse waves is that they can have a polarization. Okay, so that's basically the angle the medium vibrates at. Okay, so is it vibrating like this, or at a diagonal angle, whatever. Okay, and so you have these things called polarizing filters, and the polarizing filter has a certain angle that it allows, and then the wave itself has a certain angle. Okay, and the intensity that goes out is equal to the intensity that goes in times cosine squared of the angle, where this angle is the angle difference between the two. Okay, this is for polarized light in. If the light that goes in is not polarized, so it's unpolarized. Unpolarized means it's an equal superposition of up and down and side to side. In that case, the intensity out is half of the intensity in. All right. We talked about refraction. Okay, so there's this thing called the Index of Refraction, which is the speed of the wave of light in a vacuum divided by the speed of light in a medium. And so as light enters different media, its speed changes and its wavelength changes. So its wavelength in the medium is equal to its wavelength in a vacuum divided by n. The frequency, however, remains constant. The frequency in the medium is equal to the frequency in a vacuum. And so when light hits a boundary, okay, so on this side we have material with index of refraction n1, and on this side we have index of refraction n2. Here's the beam of light. It has an angle of incidence, which I'll call theta 1. Some of the light is reflected off of that boundary at some angle theta 3, which is called the angle of reflection. Some of the light is transmitted into the new medium, which I'll call theta 2. All right, so there's some. So the light is split up in some way that obeys conservation of energy. Some of the light is reflected, some proportion of the light is transmitted. Now, theta 3 is going to be equal to theta 1. Angle of incidence equals angle of reflection. Theta 1 is related to theta 2 according to Snell's law, which says n1 sine of theta 1 equals n2 sine of theta 2. So the amount that the index of refraction changes determines the index of refraction. All right, so that completes my review of the first semester. So I'll see you in the Zoom room.